get into the good stuff, sampling and quantization. So our discussion with sampling really should start with Claude Shannon, who we mentioned before in this class. Claude Shannon was a mathematician and an electrical engineer. He worked at Bell Labs, was an alumnus of the University of Michigan and MIT, very eccentric researcher. Once you've accomplished as much as he did at a young age, you can be very eccentric. There are stories of him riding unicycles down the halls of Bell Labs and juggling. After he wrote his very famous paper of mathematical theory of communications, he set to work doing a lot of really interesting work in puzzles and artificial intelligence. And he did a lot of good work, but unfortunately it's dwarfed in comparison to this one paper that he wrote at a relatively young age. It was published in the Bell System Technical Journal in 1948. And back then, it spelled the death knell for analog communications. It just took a long time to happen. And that was because we had to get hardware that could implement these ideas. Slowly, we began to do it. In the 50s were some of the first digital systems. Well, technically, the Morse code is a digital system, right? But really, to digitize and send raw bits, it took us quite a while to catch up to Shannon. In fact, there are ideas that came out of Shannon that were developed in the 60s that we still do not have enough hardware to implement correctly and get all the benefits that are predicted by this mathematical theory of communications. In fact, one of the reasons that digital communications just exploded in the 90s was because for the first time at the beginning of the 1990s, we had the ability to mass produce cheap devices with cheap digital chips that could do a lot of the digital processing that was required by this paper written over 40 years before. Now, why is this such an important paper? We kind of know the answer because we talked a little bit about it, but there are actually three big concepts in one paper that come out. One of them is called the rate distortion theorem. It says, given a distortion criterion, it answers the question, what is the minimum number of bits for representing a signal? That's actually what we're going to talk about today. That's the sampling and quantization issue. How do I take something that varies and has smooth behavior and digitize it? Next one, lossless data compression. What is the minimum number of irreducible bits that that can be used to reproduce a data set? That's lossless compression. It turns out that it's not necessarily the number of bits that you started with. You can actually represent something that has patterns in it with a reduced number of bits and not lose any information. That was a radical idea at the time. And then the last one, which was the one that we hit upon earlier, the channel capacity theorem. What is the minimum rate in bits per second that data can be sent across a noisy channel? And this is really what limits us in radio communications. So we wind up using all three of those in the development of a radio-based digital system. And as a bonus, he had the sampling theorem in there. It's kind of like, I'll just throw this out. We call it the Nyquist sampling theorem. Nyquist was actually Shannon's advisor, I believe, at MIT when he did his graduate work. So this is the background from where this idea is coming from. And just to get us oriented on the same page, when I used to teach an undergraduate comms class, I used to make my students memorize their Fourier transforms because it would facilitate the discussion so much better. So I could whiz around on the board and say, what's the Fourier transform of a box? And the poor undergraduate student would go, think, think. And I would test them. I'd give them pop quizzes. And so they knew about like 20 different pairs. And it made it very easy to reel off examples on the board and talk about communication systems. I will not insult this graduate crowd by doing something like that. Most of you probably know the basics anyway. So, but just to that end, I will put this up on here, a quick review of Fourier transforms. I've got two Fourier transform pairs. One is an impulse train. In the time domain, it's a bunch of little delta functions of the same value, shifted integer multiples of capital T, a period. So it repeats itself every T. And what is the Fourier transform of an impulse train? Well, it turns out to be an impulse train in the frequency domain. It's the same thing. It's a class of function that is actually the Fourier transform of itself. Can anybody name other functions that are Fourier transforms of themselves? There's more than one. Don't all answer at once. Put your hands down, and I'll call upon the first person then. No? Nobody wants to hazard a guess? I know you know some. You're just being shy. Aerospace engineers, could you shame your doubly brother? Do you know any spectral pairs? No? Okay. This was your chance to, humiliate them all. I'll give you some more later. What about a Gaussian? Fourier transform of a Gaussian? A bell curve is a bell curve. It's an interesting property of the Gaussian. A chirp function, which is really a complex Gaussian. It's an oscillating function that gets slower in frequency and then speeds back up again as it tapers off exponentially. That is also the Fourier transform of itself. There's actually a whole class of functions out there like that. It's just, again, some useful trivia to make you the life of the engineering party. And, of course, what's the Fourier transform of a box? It's a sink. So let's use those two pieces of information. Now I have this signal. A time-varying analog signal. What is this signal? It could be the intensity level of light as a camera moves, a single photodetector moves across the room. It could be the electrical signal coming out of a microphone that's picking up some noise, that transduces the vibrations of sound into electrical oscillations and vibrations. And like most analog pieces of information, we almost always approximate it as band limited. So I show in that on the left-hand side, there's the time domain signal, and on the right-hand side, there's the frequency domain. You can see I've artificially made it finite bandwidth. Start with the time domain signal, and it's band limited. Now keep in mind this is a continuous real-valued signal, which means when I take the Fourier transform, I'm just doing this as an exercise, so who knows what the actual shape of that is. There's one thing I can tell you for sure, though. Its conjugate mirror image on the negative frequency side will appear identical to its positive frequency domain. The negative frequency domain is always the conjugate mirror image of the positive frequency side of the spectrum. If the time-varying signal is real-valued. All the actual time-varying signals that we deal with are real-valued, so that better be the true of the actual Fourier transform of that signal. This is something to keep in mind. Okay. Now, let us multiply it by an impulse train. We took the time domain signal and we multiplied it by the impulse train. Now think about that, what that does. The impulse, anywhere there's an impulse, that impulse now takes the amplitude of whatever the signal was in the time domain. And then, before you get to the next impulse, is nothing. You have wiped out a non-zero interval of the function by performing this multiplication. Right? Wiped it out. So you are, even though it's an infinite impulse train with an infinite number of impulses, you have thrown away infinitely more points on the function than you have kept. Because you've only kept it at discrete points. All the stuff in between has been zeroed out. And that's represented by the left-hand sketch. Now, on the right-hand side is the frequency domain representation. What does this look like in the frequency domain? Well, we already said you multiply in the time domain. What operation is that in the frequency domain? I take two functions, I multiply them in the time domain. What am I doing to the two functions in the frequency domain? Convolution. Convolution. Because convolution in the time domain is multiplication in the frequency domain. So the two had better be switchable. Call that the duality principle of frequency analysis. Now, what does that mean? Well, that means I take my band-limited spectrum and I convolve it with the Fourier transform of an impulse train. What's a Fourier transform of an impulse train? It's an impulse train. And because it's an impulse train, it's one of the few times in your life when a convolution can be done manually in your head without even doing it, right? Because when you convolve something with an impulse, you just plop a copy down of that signal wherever the impulse appeared and scale the amplitude to whatever the amplitude of the impulse is. So unless there's impulses involved, you never want to do a convolution, right? You learned it in your sophomore year, freshman year of college, and you should never do it again unless it's an impulse. And so for that impulse train, we plop a copy of the spectrum wherever there's an impulse. And so hopefully you can see that that uniform replication in the frequency domain is equivalent to impulsive sampling. And the interesting thing about this is that if I were to take that signal and I were to run it through a low-pass filter where I just kept the center frequency spectrum, I would recover my original signal. I run it through a low-pass filter. I keep I get rid of all the copies except for the center one. Voila! I'm left with my original signal. In other words, those points that I erased in between samples don't carry any real information in a band-limited signal. The only exception occurs when those samples get too far apart. Then I do start to lose information. And what that corresponds to in the frequency domain is the spectrum. You know, if I'm taking an impulse train, I'm moving it too far apart in the time domain, that means I'm squishing the fingers in the frequency domain. And at some point, that spectrum starts to overlap. And of course, we call that airspace, guys. Aliasing. Okay, thank you for saving us, John. I was about to invalidate all of your graduate work and send you back to undergraduate school. Okay. Now, the interesting thing is that you can do this with things other than impulses. You think, oh, well, you multiply it by an impulse train. That's nice, but there's no such thing as an impulse train. Infinite voltage at one point in time, zero everywhere else. You can't make a waveform like that. Well, you could do it with any waveform. So I show here a box. I take a box, a square wave, and I multiply it. Now, again, I'm throwing away a non-zero amount of information in between my samples. But what I get is, okay, so now I'm convolving my original signal spectrum with the spectrum of the square wave. Instead of an impulse train, it's going to look like a train of non-uniform impulses, right? The spectral lines that a square wave make are going to kind of take the shape of its Fourier coefficient. It's not going to be uniform like in the uniform delta train. But they're still going to have those same spectral lines. They'll just have to be different amplitudes. And so what happens when I multiply these signals together? I plop a copy of my original signal spectrum wherever there's a spectral line adjusting for amplitude and phase. And lo and behold, look what happens. I get a bunch of copies of my original spectrum, and if I put this through a low-pass filter, get rid of all those high-frequency components, out pops my ideal original signal without any loss of data. If and only if it's a band-limited signal that I have sampled higher than the Nyquist rate, the rate that allows those spectra to overlap. Now, interestingly, there are other circuits like sample and hold, where you sample the original waveform, and then you hold that value until you need to sample again. So on the left-hand side, that's an example of what a sample and hold sample circuit would produce if that waveform would be placed in. And that's interesting from a spectral point of view. All that does is the same thing as the previous square wave component. The only difference is that now the spectrum, instead of copies of the signal spectrum, you get those copies, but they conform to the shape of a sync pulse, because you're actually dropping copies of pulses instead of multiplying by pulses. That's not a big deal because you can do low-pass filtering, a little bit of equalization. Again, you get the original signal out without any information loss. Okay. Now, and look, here's another slide. Professor Durgan is beating a dead horse. You can use triangles and do the same thing. Sample with triangles. Grab a sample and put it onto a triangle waveform. And now you get copies of the original signal at spectral lines, and it conforms to the Fourier transform of a triangle, which is a sync squared. Low-pass filter, equalize, original signal. Okay. Now, I find it doesn't really help to... It really doesn't drive things home until you actually hear some of this stuff. So I'm going to take an audio sample, and we're going to use this audio sample in this slide and in the next couple slides to illustrate these concepts, right? And this audio sample that I've got actually comes from a YouTube video produced many years ago by Georgia Tech students. It was this Georgia Tech group called the GTGs. Does anybody know who they are? Anybody here been around long enough to know who they are? They made all these videos. One of them that got a lot of airplay among the students was called The M Train. It's basically a video about how engineers should drop out of the engineering program and go into management, which became known as taking the M train at Georgia Tech. So you probably heard that expression. Did you do your undergraduate here? Okay, yeah, that's... Okay, so here's basically, let me just show you we'll do a sound check here. This is the original... Okay, this is the original clip. And, of course, here's the chorus that we'll be sampling. Why would you take the harder route? There's an easy way. Okay. You do not need to see a bunch of silly Georgia Tech students dancing around. There's a reason why they went into engineering instead of entertainment. But let me take what I have. Let's do two things to start with. Let's take that little chorus sample, and I'll play the original back just to make sure that we do a soundtrack. This is unmodified, grabbed off of YouTube. Okay, so there we go. Now, what I'm going to do is to filter this. I'm going to run this through a 20 kilohertz low-pass filter. So I've got the original audio signal, and then in MATLAB, I ran it through a filter to notch out any audio content that was above 20 kilohertz. Now, do you hear any difference between that and the unfiltered? No. In fact, I don't think the YouTube codec really captures anything much above 20 kilohertz. Your ear, except for a handful of you superhumans, does not pick up much beyond 20 kilohertz. Now, let's see. What if I filtered it at 10 kilohertz? What does that sound like? It sounds kind of muffled, right? Like somebody's got a pillow over your head. A pillow must be a low-pass filter, right? It's cotton balls, must be a low-pass filter. And just out of curiosity, let's go ahead and do 5 kilohertz sampling filtering. You can tell what it is, but we've lost all the crispness and detail. Yeah, super pillow. This is your brother. He's pressing the pillow very tightly now. Okay, so that's just gives you an idea of what the audio spectrum sounds like. I've got a picture of this, by the way. That exact let's see, how do I do this? Oh yeah, this is the exact spectrum, and you can see I've got basically 10 to the 4th hertz are the units of the horizontal axis. You can see almost everything is below 20 kilohertz. So we did the 20 kilohertz filtering. You can see you just lopped off those little lobes at the end, didn't hardly do anything. 10 kilohertz sampling. Now we see just past 10 kilohertz, we're really making it into an area where there's a lot of content. And there's still quite a lot of content below 5 kilohertz, but clearly we're getting rid of a lot of detail there. So that's just what the signal looks like. Now, let's go ahead and take a look at aliasing. What does that sound like? So remember, here's the original signal. Okay. And now let's do aliasing, where we're slowing down the samples. I'm resampling the signal, but now I'm doing it at about 10% below the Nyquist rate. In other words, those copies of the spectrum are now 10% overlapped. Just 10%. But I'm using 20 kilohertz as the absolute bandwidth. So they're intruding just a few kilohertz into one another. And then I run it through a low-pass filter at 20 kilohertz to see what happens. And this is what it sounds like. You hear that? That sounds awful. That's only 10% overlap. What if you had 100% overlap? What if you were sampling at half the Nyquist rate? So what would the Nyquist rate be? Okay, so the frequency content is 20 kilohertz in this signal. I've got to put my copy at least twice that frequency, which means I've got to sample at 40 kilohertz. Take 40 kilosamples per second. So I'm only going to sample at 20 kilosamples per second. That's going to give 100% overlap. What does that sound like? You can't even tell. Aliasing to the human ear sounds awful. It sounds awful. You could almost interpolate, or at least forgive, some of the high-frequency content that was lost when I actually removed the information. But when I aliased the signal, it was actually much worse. All the frequency content is still there. It's just rearranged in an alias signal. And it sounded awful, didn't it, compared to the filtering? Okay, so we're going to come back to that audio clip that we use as a reference, because now I want to switch into my next topic, which is quantization. Okay, I've taken whatever analog medium I'm working with. Maybe it's video, maybe it's audio, maybe it's some scientific measurement. Maybe it's an image from a camera in a project. And I've sampled it, and now I have to digitize that sample of data. And this is a very interesting philosophical point. I could take a finite subset of that function, sample it with respect to time along the horizontal axis, and I don't lose any information. But I will always lose information when I quantize it, no matter how fine or close my samples get. The amount of information loss is smaller and smaller, the amount of distortion, we would call it. But I always distort when I effectively sample in the vertical axis and not the horizontal axis. That's interesting. That's interesting to ponder why the world is like that. But an example of a quantization scheme, and the simplest one that I could think of, is this scheme right here, where we've got a signal, And you see I've drawn a grid there. There's a grid there of 1, 2, 3, 4, 5, 6, 7, 8 levels in the vertical axis. And the vertical lines are where I'm sampling the function. So I have to pick out a value to sample it, and then I have to snap it to a quantization level. And because I've got 8 quantization levels, it would be natural from a binary perspective to represent that with 3 bits of information, right? 3 bits gives me 8 combinations of numbers. There are 8 combinations of 3 bits that I can make and assign to each of those levels. And that would essentially digitize this information. I would take each sample. I would give 3 bits that could represent that sample. And I send it along its merry way down the digital information channel that I'm transmitting. And we call this uniform quantization because the way that it's sketched out, the levels are uniform. They're equal spaced. Those are the easiest kind of quantizers to design. They're not always the best quantizers. Why? Because they presume that the signal that you're quantizing has uniform amplitude statistics. And very few signals actually have that in nature. You take human speech, for example. If you were to plot the histogram of amplitudes coming out of a microphone, the voltages coming out of a microphone, what you would find is that it's kind of a bell curve with maybe some stretched out tails. Why? Because human speech has a lot of like low frequency content that's always ubiquitous and present at all times, and a lot of zeros, a lot of downtime also. And then there are these high frequency events in speech, like plosives. Everybody know what a plosive is? Plosive is it's an exploding noise that comes out of your mouth when you make things like P's, D's. John Luke is like, I can feel the plosives. Back off, Professor Durgan. So anyway, that beckons a different strategy that we'll talk about in a second. But what is the distortion that we're going to introduce? Well, here I've got an example here, an illustration of a signal that's been uniformly quantized. And, of course, in the absence of the stuff in between and an infinite number of levels to snap to, I get this kind of rough, blockish representation of my signal. And if I take that blockish signal and I subtract it from the original analog signal, I can view that as a sort of error signal, as basically a measure of distortion. That's what that bottom graph is. It's the quantization error. And in some ways, I can actually compute a signal-to-noise ratio based on that, right? I have a signal power, and then I have noise power, which is however big this quantization error is. And it makes sense that the more states that I add, the more bits per state I can use to represent quantization, then the smaller that quantization error is, and the higher the signal-to-noise ratio is. Now, keep in mind, when we talk about signal-to-noise ratio of a quantized signal, that has nothing to do with the signal-to-noise ratio of a communications medium. We're using the same construct to represent equality of the signal. But keep in mind that I can quantize an analog signal. It will have a quantization SNR. And no matter how clean the channel is, no matter how error-free my transmission is, I will always have that quantized SNR with me. I'll never do better than that. That basically is going to be the difference between the actual signal and my reconstructed signal, the best I could possibly do. Okay, so now, here's the fun part. Let's go back to our audio clip. And I'm going to show you different levels of quantization and how it sounds. So let's go ahead and let's see. Oop, that's not what I want to do. Let's go ahead and look at the effective quantization level. So here is the 8-bit quantized version of that exact same clip. That means there is 2 to the 8th quantization levels per sample. 8 bits is that's 256 levels. What does it sound like? It sounds pretty much like that. On this extraordinarily high-class, high-fidelity audio system in this classroom, state-of-the-art, beyond imagination, it sounds about the same as the original, right? So let's do 6-bit quantization. This is 2 to the 6th. Let's see, that's what? 64. 64. Can you hear a little bit of difference? I think some of you can, yeah. Let's do 2 to the 4th. That would be only 16 states, right? 2 to the 4th is 16. You kind of hear that quantization. It's coming. It sounds like white noise. It's not like additive white Gaussian noise. It has different statistics, but it kind of feels like that, right? Like I'm listening to a really crummy AM transmission. Anybody want to do 3? I've only got 8 bits to work with, 8 states. Would you 2? Do you think that's even worthwhile doing that exercise? 2, 4 bits of quantization. Very crummy, but interesting that you can still make out what's going on. Your ear is remarkably good at pattern recognition in noisy environments. So at this point, the signal-to-noise ratio is garbage, right? It's very low. But you can still make it out. In fact, you can make it out so well that it tempts one to try an experiment with 1-bit quantization. What do you think that's just 0 crossings at that point. That's all you're measuring in the signal. When does the signal cross 0? Or estimating when it crosses 0. Do you think you'll hear anything? A human ear is amazing, isn't it? That should be a signal-to-noise ratio of only 6 dB. The errors are getting almost the same order of magnitude as the signal itself, the quantization error. But you can actually pick out what's being transmitted. Difficult to listen to, but one might argue this clip is difficult to listen to with extraordinarily high signal-to-noise ratio. So, okay. Now, properties of a uniform quantizer. You can span either usually 0 volts to some sort of maximum voltage, or another flavor of that same quantizer will span negative volts to some positive volts, maximum, minimum, depending on how you've worked it. The number of levels is related to the number of bits per sample, of course. If you have m bits per sample, then you can have 2 to the m uniform levels. That's pretty standard. The spacings, of course, is the max minus the min divided by 2 to the m minus 1. And this is the most important one, the quantization signal-to-noise ratio, if you work it out in an ideal uniform quantizer. What makes an ideal uniform quantizer? The quantizer has uniform levels, and the signal has a probability density function, a distribution of amplitudes that matches that uniform range. If that's the case, then you can achieve up to 6m in dB. That's in the dB scale, where m is the number of bits. So if I have that 1-bit quantizer that we ran at the end, my signal will still be about 4 times that power as my quantization error. If I've done everything to maximize the use signal range, and if I've actually matched the distribution of the signal to the uniform stretching of my quantizer. I did not do those things when I did that at MATLAB. So the signal-to-noise ratio of that 1-bit quantized signal is actually probably much higher, or much lower than that. much lower than 6. But if I have m bits, then I can have 6m in dB signal-to-noise ratio in the ideal case. If my signal is non-uniform, I can still use a uniform quantizer because they're so easy to build and they're the most generic way to quantize something. But I must compand the signal at that point. What is a compander? A compander is just a device that non-linearly maps the input voltage to an output voltage. So here's an example of one. I've got a signal at the top that has, you'll notice it has some pretty high peaks. If I ran that through a uniform quantizer and tried to match it and get the distribution to work out, I'd probably wind up clipping that signal because these rare peaks that don't occur very often but still need to be quantized occur beyond the limits of my uniform voltage quantizer. So if I ran it, however, through a compander that had this characteristic that basically smashed down those high peaks, I would have a signal that probably looked much more uniform. I could quantize that. I could transmit it. And when I went to reconstruct that, if I wanted to reconstruct the original analog signal, I would just have to reverse compand, right? I would have to basically take that analog signal, run it through a device that had the inverse characteristic that bent the signals the other way on the output, and I would reconstruct this signal. It's a very useful concept. It was used in telephony all the time. In fact, I think it's still quite commonly used in telephony because we still have a lot of analog voice channels that leave your house and go to a quantizer before it hits the main public switch telephone network, the wires in your neighborhood. It's also actually this is the same concept of linearization of a power amplifier that we'll talk about later for any of you who've studied those things. And for non-uniform quantization, an alternative to companding is to just design a quantizer that has irregular quantization levels that match the distribution of your signal. If you know what the PDF or the distribution of your amplitudes in your signal is, there's this thing called the Lloyd-Max algorithm, an iterative algorithm for finding the optimal quantization steps. And you can do that if you don't want to just get an off-the-shelf uniform compander. And we won't get into this at all, but just be aware out there, there's also this thing called vector quantization. And this is basically the one way that we know of how to actually approach the predicted mathematical limit by that's included in the Shannon rate distortion limit. So if you do the best possible quantization job you can, like say you've made your signal so that it has uniform statistics, you've applied a nice uniform quantizer to it, and you find you get 6 dB signal-to-noise ratio. You still wind up being like 7 or 8 dB away from what the mathematical limit predicted by the Shannon rate distortion limit. You say, well, what else can you do? Well, one technique is this vector quantization. So if you imagine 2 samples, let's quantize 2 samples at the same time. How would we do that? Well, on the left, you can see I've got a 2-dimensional graph now. And you can think of one dimension being sample number 1, and then the next sample, sample number 2, would be in the vertical dimension. And if I applied a uniform quantizer to those signals individually and in succession, then you can think of the quantization space as being this uniform grid, right? Every uniform level of the first sample is on the x-axis. Every uniform sample of the second sample is on the y-axis. And the intersection points trace out a grid. And those are the quantization levels for those pairs of samples. And I can do that independently. I can work on one sample and quantize it, and I can work on another sample and quantize it, and that's how I can represent it on a 2D graph. Or I can get a little creative and rearrange my samples in space so that I do not have a nice grid. So I cannot, in this case, I cannot pick a point in that space and snap to it, independently processing sample 1 and sample 2. I have to have both of those samples at the same time. But if I do that, I can rearrange a non-uniform grid and kind of snap to those points, and that will actually lower my signal-to-noise ratio in terms of quantization. Now, to really get gains in this, I have to do lots of samples at the same time. And in fact, it's often beneficial to not quantize and sample separately, but if you know what the mathematical structure of your random input data signal is, the types of statistics that it has, you should actually do those things together. You know, don't necessarily sample or quantize uniformly. Do all of your quantization kind of with a big picture view of what the signal is. The more jointly you can, the more information or the more section of the signal that you have when you do sampling and quantization, the more big picture, the less distortion you can wind up introducing into a signal. And that's how you approach some of these fundamental limits. This is the frustrating thing about Shannon's original paper. It gave all these wonderfully derived mathematical limits for communicating, but it tells nothing about how to get to those limits. It's sort of like saying, well, you can't go faster than the speed of light. Get to it, aerospace engineers. I want 0.9 C by tomorrow morning. But it's nice, though, because at least the problem is a closed problem, right? There are very few engineering problems that are actually like that. We know what the right answer is. You just have to design to get that. So when you're done your design, or you think you're done as a student, you know how close to the right answer you've gotten. Very few design problems are actually like that. In some ways, that has kind of spelled the death knell for physical layer research in telecommunications. 20 years ago, we'd had half this room, half the grad students in this class would be researching ways to digitally modulate physical bits on symbols and things like that. And by and large, there's still a lot of active research problems in there, but the share of electrical engineering research of that type of problem has dwindled dramatically because we actually can get really close to the Shannon channel capacity now. We have so many tools in our arsenal as communications engineers for quantization, sampling, transmission, coding, error correction coding, all these different techniques. And we kind of, it's really more about applying and picking, knowing which tools are appropriate for a scenario rather than trying to research tools on how to get to this functional limit. Yeah, Jean-Luc.
I wanted to ask you, how are the cell phones sampling and quantizing? How do they communicate in real life?
How do cell phones sample and quantize voice, for example? Yeah, real time. So this is a really good example of what I was talking about in terms of trying to capture, sample and quantize with a minimum number of bits what voice sounds like. And the cell phones, there's been a tremendous amount of research put into what's called the vocoder, the voice encoder, which the first step is basically sampling, quantization, and then some compression. And a lot of vocoders are actually designed to the native language that they're supposed to operate into. So, for example, there's an English language vocoder that's loaded onto all the cell phones that are expected to operate in English. If you want to operate in Russian or Spanish, you'd actually use a slightly different vocoder that takes into account that the distribution of amplitudes and the occurrence of different things look differently and sound differently in those other languages. And you sample, you quantize, and then you also encode based on those patterns and bring it down to, I think the bit rates have gotten as low as 8 kilobits per second to represent speech. So think about that, 8 kilobits per second. We said that you could hear up to about 20 kilohertz per second. 20 kilohertz per second. So you got to sample that analog signal 40 kilohertz per second. And we said we didn't hear any distortion when we heard that 8-bit per second. I mean, it wasn't a great audio quality, but you could carry on a conversation at 8 bits per sample. So doing the math on that really quick, we should be sampling at 300. We should be transmitting at 320 kilobits per second. But I'm telling you that the vocoder in the cell phone operates at 8 kilobits per second. And there really isn't that much audible difference between the thing that I played that you should have done at 320 kilobits per second and the 8 kilobits per second. Where is all that coming from? It's coming from compression, which we haven't talked about, but it's also coming from optimization of the quantizer and the sampler inside your phone. Does that roughly answer your question? Kind of gives you some order of magnitude. Good question. Good question. Always important to take these technologies show up in your daily lives, and it's always good to get some numbers and some feel for how that stuff is working. Let's say I wanted to digitize analog video. Here's another example we can work through. So this is actually a very common thing. You want to take we have a tremendous amount of archived analog video, but we want to digitize it and save it or transmit it on a satellite link. Analog video has a 5 megahertz baseband bandwidth, so I must sample it at 10 megahertz if I want to obey Nyquist. So 10 megasamples per second. Let's assume 256 level quantization. It turns out that 256 level quantization is not very good for your hearing. You can actually still hear, if we actually had a good speaker system, imperfections in the audio. This is one of the reasons why a compact disc player, I think they use, is it 12 or 16 bits per sample? The SNR is all the way down at 96 dB. So that would imply, what is that? 16-bit quantization. Because the human ear can hear imperfections at SNRs up to about 60 dB. And some people are audiophiles and probably can do a little bit better. And then you've got to have some room for dynamic range. So the compact disc is significantly over-designed in terms of its quantization levels. But here, video is very forgiving. Your eye is very forgiving. And so we're only going to use 8 bits per sample. Visible SNR of 8 and 48 dB in terms of quantization noise. That'll produce a pretty good picture. Requires an uncompressed bit rate of 80 megabits per second if we do it that way. 80 megabits per second. That's still too fast for most of your wireless connections nowadays. We've been leaps and bounds in wireless technology and networking since I put that slide together 7 or 8 years ago. But we still have trouble keeping up with 80 megabits per second if that was your transmission rate required to maintain a video link. None of your home routers could do that probably. And AT&T would probably charge you millions of dollars a month to maintain that rate. And that's to digitize a crummy analog picture. That's not even talking about a nice high-definition picture. So, and there's no slide after this. So wireless communications is hopeless.